Hi, welcome to the Signal Path. In this episode, we're going to take a close look at the brand new Siglent SVA1032X. This 1000X instrument series is a both spectrum and vector network analyzer that Siglent has released, and they're really proud of it because they believe it's a disruptive instrument on the market given the price-performance ratio that it offers. I'm going to take a detailed look at this. As always, this review is going to have a teardown. I'm going to show you how the instrument works in detail, and then we're going to put it through the test, trying out all the different software options that are built in it. They've done some clever design internally as well. And of course, the software is going to give you advanced measurements and even has demodulation capabilities, digital demodulation capabilities that I want to show you. By the way, Siglent is also known for their excellent web servers that are built into the unit. I'm not going to go through the details of that because it's been covered in some of my other videos, but this is also a really nice feature. Once you hook this up to the network, you can directly interact with it real time, and basically you're looking at the same screen as the unit, which is a nice feature. In terms of design and in terms of looks and feel, I think it's really good. The LCD screen is a non-reflective, has a high contrast ratio, visible at good angles, and no instrument screen should really be reflective ever. There's a power button, USB, and a headphone jack for listening to demodulation signals. Both of the ports here are type N, port 1 being the tracking generator source and the port 2 being the RF input, allowing you to measure S11, S21, and of course all kind of spectrum analysis. The choices of the buttons and the feel of the buttons is very good. These are all the buttons you would expect to find on a spectrum analyzer. All the network analyzer buttons like sweep type and stimulus and power and all those things are done with software. They're not actually represented as a button here. This is because the buttons are exactly like a spectrum analyzer. Contextual buttons in the front for what's on the screen, auto tune button that nobody ever uses, tracking generator that lights up, and a mode button that lights up showing you that you're in a different mode of operation when you're doing something else other than spectrum measurement. And there is nothing really surprising in the back of the unit. Power, of course, coming in over here. Lock is available if you need it to. And then over here we have USB and Ethernet standard, reference input and output, and a trigger input. So really nothing unusual. Like I said, it's really compact. Handle is there. You can kick it up so it stands at an angle. Yeah, no complaints. And here's the main RF port for the SVA Spectrum Analyzer Network Analyzer Hybrid. And as you can see, the board resembles a very traditional digital spectrum analyzer architecture. And we're going to go into the details of that. There's a separate board over here, and you can see it is temporarily connected to the main board. And this is the tracking generator portion. It is clever to have the entire thing on one panel and then simply break the boards apart and then connect them with ribbon cables, which is how they're connected when they're inside the instrument. And this also saves a lot of space. You don't have to throw away this entire piece. So they've obviously thought a lot about that. There are a lot of components in here and many RF paths and different IF paths happening at the same time. So we're going to have to talk about that and some clever designs that go into the heart of this to be able to get network analyzer functions out of what is, on the heart of it, really a spectrum analyzer. So we're going to take a look and see how that looks like. I think it's easier to take a picture of this and then just trace out the signals. It would be a little bit, I think, quicker to do that. You can also see a few other minor things. 2 screws missing from these connectors. These are most likely to fasten them to the chassis. So you have 2 screws to fasten it to the PCB and the other 2 screws to the chassis. This is also fairly common. There aren't really much on the other side of the board. Everything is really on this side. This is a hybrid PCB. So you can see if I look at it from the side, you can clearly see that there is a different layer on top of this PCB, and that's because that's the RF layer. These hybrid PCB stacks are very common and then done all the time in radios and devices like this. On the other side, you can see we have a few connectors, which you can also see from the other side because there's a through hole, and mostly just really blank and the ribbon cables that connect the 2 sides together. So let me go and take a picture of this, and then we can analyze it on the computer. So let's go over the design of this entire spectrum analyzer, and I want to tell you exactly how it works and how all the different components interact with each other. The easiest place to start is the RF input, so let's go from there. The very first thing the RF input sees is a DC block. This is also very common. The DC block is going to separate all of the DC components of the input of signal from the instrument, protecting the instrument from any problem that a large DC signal might pose. And this particular device has a breakdown of about 30 volts, and that's the breakdown of that capacitor. Anything above that, then the capacitor will break down and the DC will enter the instrument. Having no DC makes things a lot easier. You don't have to worry about protecting the devices. You also don't have to worry about going very close to low frequencies, and that makes things a lot easier for the design of the up and down converters as well. The disadvantage is that then you cut off all the low frequencies, and this particular instrument does not process anything below 3 kilohertz. You can imagine how hard it must be for some of the advanced spectrum analyzers that go all the way down to a few hertz at the same time also doing signal analysis all the way to tens of gigahertz, and that's going to be a very complex input protection circuit indeed. The next thing we're going to have is a bunch of diodes, and these are not populated. These are going to be diodes to do surge protection and eliminate any high power signal going in by clamping it. Now they haven't populated this either because they feel like they don't need to, or they didn't want to pay the penalty for the frequency implications of having the diode directly on the RF input. And there's some linearity limitations as well, especially at high input signals. After that, we're going to hit our first switch. This switch over here is an HMC1118. Everything on this board is actually from Hittite, analog devices basically. And this switch is going to allow two separate paths to be selected. One path is this way, and the other path is this way. Now I'm going to keep this path towards the end because there's a lot of stuff happening before we can explain what this does. And this is where actually some signal comes into it, which means that this front-end switch allows the signal to be injected into the RF path or the main RF input to be selected. Well, that's pretty interesting. So here's the first RF. Let's just forget about that for now. And we're going to go and hit our first switch over here. The second switch, I should say. This switch is going to switch our attenuator in and out, and it gives us two paths, either a straight path or a 20 dB attenuation path. And then we go through another switch again. So they're going to put the 20 dB attenuator first, and that makes sense. Why? Because if you have a large signal coming in, you can quickly switch in a 20 dB attenuator, and that's as close to the front of the circuit as possible, protecting everything afterwards. This also means that the design of the next stage attenuator becomes a lot simpler, because if your signal is strong and you already have the 20 dB attenuator in the path of the signal arriving at the attenuator afterwards is much, much smaller. Any other way, and it would be just a silly design. So the next stage here is our digital attenuator. This digital attenuator is a PE43711, and this is going to give you a fine dB resolution for doing very small steps in the input attenuator. You can select that from the GUI, of course. Now after this, we're going to have yet again another switch here, another switch here, and either a path through an amplifier or a straight path going forward. Now this path through the amplifier is the preamp, and it's going to give you maybe 10 or 15 dB of additional gain. It's going to lower the displayed average noise level of the instrument because it lowers the noise figure of the instrument. Now you're going to put that all the way at the end again to protect it, and also to have the best possible linearity if there are attenuators switched in. But normally if you use the preamplifier stages, that's because you've already set all of the attenuators to 0, and all you have left is the signal you want to look at. So over here is some control circuitry, some digital stuff, nothing really that exciting. After that, we have a low pass filter. This low pass filter is going to get rid of everything above 3.2 gigahertz. And the reason we don't do that is because the next stage followed is an upconvert mixer. An upconvert mixer, of course, is going to push all the frequency above 3.2 gigahertz, and that allows us to be able to filter it very effectively, getting rid of all the spurious tones that we don't want. This is pretty attractive, and this is a very common technique also for have a front end of a spectrum analyzer to upconvert first before it downconverts, and this is the reason why. And then over here, you can see some LC components that are this distributed LC filter you have on the PCB. Fairly high quality factor, directly done on the the high quality factor part of the PCB, as I spoke about it earlier. Now this is a mixer. This mixer is an HMC557A. And this mixer is going to have an RF and a low and an IF, of course. So the IF is coming in, that's the signal that you're injecting into the spectrum analyzer. It's going to have an LO coming over here. So that LO we're going to talk about, that's a whole other section of the circuit. But the RF coming out is now going to be above 3.2 gigahertz. And because this mixer has some conversion loss, we have an amplifier here to boost that. And then we have a bandpass filter over here that's going to get rid of all of the frequencies we don't want, and that's going to go right through over here. Now we have a frequency that's above 3.2 gigahertz and filtered already. Now we can finally begin to do down conversion, because we cannot analyze that signal as it is. It's going to require a ridiculously high sampling rate analog to digital converter, or a digitally sampling one. You don't want any of that, so therefore we're going to down convert the signal again, in all the way until an IF frequency that we can analyze with an analog to digital converter. And therefore we're going to need another mixer. And this mixer over here, this one is an HMC213B, and this is going to bring our frequency down. Just like the other mixer, is going to need an LO and an RF and an IF. And here, in this particular case, its IF is going to come down from here, and its LO is coming from a whole other circuit yet again, a whole different LO domain that's separate from the first one, and we're going to talk about that later as well. And the signal from that is now going to go through two SAW filters. because you have already down converted it to a lower frequency in a couple of hundreds of megahertz in this case, you can do a bandpass filter around it with SAW filters and really clean it out before you put it into the final IF. Once you put it in the final IF, the frequency becomes really low, and then filtering would have to be done with discrete components. And then afterwards, we're going to have another mixer. This mixer over here is a mini circuits ADE-2. That's going to bring our frequency really low so that it can be analyzed by the ADC, but not before going through to some more LC filters and some more switches and some more switches yet again, and then finally reaching the connector. This connector over here is our IF connector. The switches here, some components are unpopulated, and that's probably because they either didn't need to populate it, or they have different models, or they figured out that they don't need as much filtering. There are many reasons why this can be the case. By the way, there's some more switching happening over here, but the entire RF path is now shown in red. And if you look, this occupies a tiny fraction of the board. That's because almost everything else is actually LO, and the LO is really critical because any imperfection of the LO signal shows up in your measurement. You cannot separate them from the RF, so the LO has to be so much better than anything else in the device. Otherwise, what you're going to end up measuring is the LO signal and not the RF signal generated by the circuits that you want to actually measure. So the LO distribution network becomes therefore quite interesting. So let's talk about the LO distribution. We know that there are three components that require the LO on the RF board alone. We need an LO signal for this first up conversion mixer. We need an LO signal for the first down conversion mixer and an LO signal for the final IF mixer. And we have to make sure that all of these LOs are coherently locked to the same reference, because if they're drifting with respect to each other, you definitely would not be able to do any network analysis, and you certainly wouldn't be able to do any good spectrum analyzer measurement. So we have to figure out where all of these going to come from. First, we need to identify the reference. The reference is coming from here. That's our 10 megahertz input. And there's a clock buffer over here. This clock buffer is a CDCLV C1106, and that's going to buffer and distribute the 10 megahertz clock into multiple places at the same time. And one of the places it goes to is into this connector, which then ends up all the way down here for the tracking generator, which we'll talk about at the end. So that's where the 10 megahertz reference comes from. That's how the absolute value for all the synthesizers on this board are going to get their reference from. Okay, so let's start from this one. At the heart of this first LO, we have this ZCOM VCO. And this voltage controlled oscillator is between 2 to 4 gigahertz. This is a V600 ME14. That's going to give us a signal between 2 to 4. I'm not exactly sure what range they're using, but it's trapped between those two extremes. And that's going to end up somehow all the way up to there at the mixer. The very first thing is that it's going to go through a coupler. That coupler is used to lock the VCO to a PLL. We'll get to that. And then there's a little amplifier over here, and then it goes to this section. Now this section, you can see there's a part that's not populated. There's a straight path over here. There's a path that goes through this component, and they can configure how they're using it. So they have probably two different parts that they can use as a doubler. Depending on which one they have available, they can populate two different versions or two different footprints here. This guy over here, this is a frequency doubler, and this is an HMC 189A. This is an active doubler, also from Hittite. By the way, everything on this board is, again, as I said, from Hittite, and they're all gallium arsenide and almost no silicon on this board. Anyway, so after that doubler, we have now a frequency that's multiplied by 2 coming from the VCO. But of course, that frequency is not pure, because it's going to have harmonics not only from the VCO, but also from the doubler. So the fundamental is going to be there, the doubled frequency is going to be there, and all the intermodulation products between those frequencies are going to be present. You definitely don't want those to reach the mixer, because they can down convert on top of each other, and then you're going to get just an absolute mess of signals going into the final IF. So you definitely don't want that. And the way to avoid this is that as the VCO sweeps across its range, the harmonics are also going to sweep with it. So depending on what frequency range the instrument is running at, you can put it through these switches, and then you can put it through unique filters, and these filters will then get rid of the tones that you don't want. So that is quite beneficial, because this allows you to get rid of all the harmonics and keep as pure of a tone as you can going into the next stage. The disadvantage is that these are all going to be lossy, so you're going to have to spend some more power and re-amplify the signal. And they do that, of course. You can see there's an amplifier over here, and then they take that out. And there's another amplifier right over here. So they have to boost this up quite high, because this mixer requires a very high LO power. You can also see occasionally some of these connectors, and these connectors are for testing purposes. You can populate them and then move some passives around, and then you can reroute the signal to those connectors if you need to test them separately. Now the output of that then finally goes through here and then eventually reaches this mixer up here. So that's one of the domains of the LO. Now every time you see a VCO or a PLL or a frequency multiplier, you're going to have a very clean power supply next to it, because if you don't, any noise on the power supply is going to show up directly at the carrier frequency, directly at the RF signal coming out of the mixer or the RF signal coming out of the synthesizer. That's why they're all accompanied with very, very good voltage regulators. These voltage regulators are all over the place. This particular one is an HMC 976 down here, and up there is an HMC 860. Band gap reference and multi-output voltage regulators ensure that you have a very quiet power plane of these different components, and that those power planes are isolated from all the other power planes and from all the other synthesizers, so you don't have any frequency pulling and pushing. You don't get any pollution of the signal. This VCO by itself is unlocked, of course. It's going to need a synthesizer. That's why there's a coupler here, an amplifier to boost it, and that goes into this synthesizer. And this synthesizer here is also a Hittite part, HMC 703, and that together with this VCO is going to give you your first synthesizer, which is doubled to the first mixer. Okay, so that's one LO domain, but that doesn't take care of the other mixers. You're going to need whole other LO domains for that, and that one starts all the way up here. And this one up here is an HMC 835, and the difference is that this one has a built-in VCO, is a complete synthesizer, it's not just a PLL, and you can see again it's surrounded by very high quality voltage regulators as to be expected. The signal from that goes through this coupler, is boosted again, and then goes through this filter before it reaches the second mixer of the instrument. Now there's also a coupler here, just like the other one, but this coupler has a totally different purpose. This is a full synthesizer, so it doesn't need a coupler to lock the frequency. It needs it because it is using a sliding IF super heterodyne architecture between this mixer and this mixer. That signal then gets amplified, it gets divided by 2, and then it goes over here and then eventually reaches this mixer. So think about what's happening here. The output of this VCO at the fundamental goes to this mixer, but then the coupled signal is amplified and divided by 2 before it reaches the next mixer. That's what makes it a sliding IF super heterodyne architecture. So that's the LO of the other one. And if you look over here, there's another coupler here. And this coupler over here takes a signal and actually feeds it into this connector. And this connector, well, where else would it going to go? It's going to go to the tracking generator. That's the same as the connector over here. And this allows the signal from this to be coherently, as the instrument is sweeping, to be passed onto the tracking generator for the tracking generator to use to create a signal itself. Now there are some complications here. Let's jump into the tracking generator's LO generation itself and see how that works. Keep in mind that this LO going into this mixer is not sweeping the same frequency range as the instrument itself. It's not going from 3 kilohertz all the way up to the frequency of 3.2 gigahertz. It's not doing that because it's doing an up conversion, which means that this signal is useful for the tracking generator because it allows it to track, but it's not the signal you're looking for because you need to create a lower frequency version of that signal that's going in sync with this. That's why the tracking generator has its own entire synthesizer again, which is identical to the synthesizer up there. It's an HMC, which one was it? I've lost track of what I'm looking at here. It's an HMC 835, and that allows this to be an independent synthesizer, again with its own voltage regulators nearby, and that goes over here and goes into this mixer. So therefore the LO signal from here, amplified, and going in here, is now going to create the signal exactly in the frequency range that the tracking generator needs to generate. And that frequency range is the desired frequency range of the TG within the frequency of the spectrum analyzer. So everything we talked about here so far is all about spectrum analysis. None of this discussion has anything to do with vector network analyzer. So how does that happen? Well, for that, you're going to have to do some clever work here. And this is what they have done. Think about what happens for this LO signal. I'm going to draw a different color here. This LO signal goes over here. There is an attenuator here. This attenuator just controls the output power of the tracking generator. That's normal. And then we have switches. We have a switch here. We have a switch here. We have a switch here. So, and then there is some amplifier over here. And then there's a signal eventually makes it here. So if you think about what's going on is, how do I do network analysis? What I need to do is I need to measure the signal that's going to the output of the network analyzer at the same time as I'm generating it, because it's going to tell me the standing wave ratio. If I want to know VSWR, that's how I need to do it. I need to measure the signal that is happening at this port in order to find out exactly what is the return signal coming back into the instrument and creating the S11. I want to measure S11. But if I want to do that, I would have to calibrate this, which is exactly what this instrument does. So by using a combination of these switches, I can reroute the signal to different loads, as well as combine them with the software and the calibration kit in order to measure all the different combinations of phases that are going to be present here in order to be able to do my calibration coefficients and then put the equations in and measure my S11. But then how do I measure the signal here? Well, what is the easiest way to measure the signal? You can measure this signal using the spectrum analyzer itself, and that's the clever part. You can reroute the signal to this connector. This connector is then connected to this connector, and that signal is then going over here. And that's how the entire loop closes. So the signal coming out of the TG is simultaneously being fed to the input of the spectrum analyzer and going through this entire section. And with the calibration done earlier, you can finally do vector measurement. And this is why this instrument can only measure S11 alone by itself, because as soon as you want to measure S12, the situation is totally different, or S21, the situation is totally different, because then you're going to have to go from one port to another, and then you cannot use this path anymore. That's why it does one measurement at a time the way it does it. So there's a coupler here. It's a passive coupler in the front end, and that allows you to inject a signal and simultaneously pick the signal back up, and then with the calibration coefficients you have computed earlier, do your complete S parameter measurement. So the system is very clever, and the only difference between this and a spectrum analyzer is in some of the ways this orange section and some of the ways this synthesizer section over here works. Otherwise, this is identical to a regular spectrum analyzer. The cleverness is in the design of the RF section here, as well as the design of the software, of course. Now there is another path here that goes over here. I'm not 100% sure what this path is for. It could be for some calibration, it could be related to the network analyzer measurement. Not quite sure yet exactly what's going on with it, but anyway, it goes over here. There's another switch there. And there's also an Altera Max over here, and this one just controls everything. That's a glue logic connecting everything together. And there it is. That's everything about this board. It took a long time to explain, and I didn't really explain everything about it, but hopefully you have now a reasonably good idea of how that unit works. Now, the other thing that is a little bit surprising is that because this synthesizer is completely independent of the synthesizer up here, I'm curious why they don't have the option to allow you to independently set the tracking generator frequency, or set the tracking generator frequency with an offset with respect to the carrier. So then you can do offset tracking, or you can do an independent synthesizer just by itself. I'm not sure why they haven't put a switch over here and just allow you to switch into this path separately. Obviously you cannot, this cannot be there, because if you're sweeping, this is going to sweep. So the only way to do this is to independently set it by this guy. And you could have done that with a switch over here. So I'm curious why they haven't done that. It seemed like a low-hanging fruit in my opinion to add that functionality. Roden Shorts, for example, has an independent synthesizer in theirs. So the instrument takes about 19 seconds to boot after you turn it on, which is good. It's ready to use fairly quickly. And once it basically boots up, what you're getting is a spectrum analyzer screen. In fact, if you never press the mode button and choose one of the other modes, you may not even know that this thing can do network analysis. But indeed, it can do vector network analysis, it can do distance to fault and modulation analysis, as well as a basic spectrum analyzer. The GUI gives you all the different settings you would want at a glance, which is good. Gives you start, stop, sweep, resolution bandwidth, video bandwidth, sweep time, as well as what kind of trace you're viewing, and the trigger functions here, the word free, I think you should say free running. So, and then of course attenuation. It boots up with the attenuation at 20 dB, which is good. You don't want this to be at 0. It just protects the instrument a little bit more that way. So I think it's quite nice. Now, there's a couple of things I always do before I do extensive testing is to do some of the basic measurements. You know, how does the instrument deal with overload condition? What is the quality of the tracking generator source? What kind of phase noise we're dealing with on this, and just some basic GUI manipulation. And then we're going to do a big experiment where we try every one of these different functions on that particular setup that I have put together, and we can see how well this instrument works and how easy it is to perform various functions. And for the first setup, I'm just going to simply connect the RF output of the EXG vector signal generator directly to the SVA1032X, and we can see how it handles large signals. Now, one thing I didn't mention earlier is that this instrument has a touchscreen, and you can then touch the touchscreen and enter any value that you want, and the GUI works reasonably well with it. I just don't want to use that because I don't want to constantly bring my hand in front of the screen, but I'm impressed how well the touchscreen works on this unit. Let's go ahead and inject some signal here. Now, before I do that, I'm going to change the input attenuation. You can see that 20 dB. I'm going to change the amplitude over here, attenuation. I'm going to enter 0 instead. Now, this removes all the front-end attenuation and makes the front-end most vulnerable for distortion and for overload. Now, at the same time, the instrument changes the reference to minus 20 dBm, telling you that if there is any signal above minus 20 dBm, we should suspect it. But it seems really aggressive, and I want to know if it will give us some warning if the signal is too big. Let's go ahead and enable a gigahertz tone here. Here's a 1 gigahertz tone. I'm going to do a peak search. At the same time, I'm going to do a continuous peak, so this instrument will follow the peak no matter what frequency it's at. There it is, it's measuring minus 25.6 dBm, which is correct. There's some loss in the cable, and that accounts for the half a dB of loss. Let's increase the power. I'm going to go to minus 20 dBm, and minus 20 dBm, we are right at the reference, and it is measuring it correctly. Now I'm going to go above the reference. Here's minus 15 dBm, seems to be okay. Here's minus 10 dBm. We can see some second harmonic creeping up, but it's still measuring, it's not complaining. Minus 5 dBm, still no complaint. Two large tones appearing here. And minus 3, there you go. It's beginning to complain at minus 3 dBm. So let's back that off to minus 5. So at minus 5 dBm input, it is measuring the correct value, but we see two harmonics. Now, are these harmonics from the synthesizer or from the spectrum analyzer? You don't know, and we're going to find out in just a second. But we are well above the minus 20 here, and it didn't complain all the way until minus 5. Let's go ahead and add some attenuation. Now, if I add attenuation and these harmonics go away, then it's the instrument that's generating them, not the synthesizer. Let's go ahead. I'm going to enter the attenuation of 5 dB. There you go. You can see that they disappeared. And that tells me that indeed it's the nonlinearity of the instrument that is causing it. So it should warn you a little bit earlier, but it doesn't. Let's go ahead and let's back this off again to minus 15. And let's change the frequency from 1 gigahertz to 3 gigahertz. That makes things quite a bit harder for the instrument because now the losses of the front end are much higher. So it is harder to detect that the analog to digital converter of the IF section is being overloaded, and you cannot tell that the front end is becoming nonlinear. And I'll show you. Let's go ahead and increase the amplitude again. We're going to go to minus 10. You can see we're well over. At minus 5, it's still not complaining. At 0 dBm input, it's still not complaining. But look at this. This is a subharmonic being generated. I'm going to increase it to, there it is. So I have to hit values as high as 2 or 3 dBm before I start seeing a problem. Now, this is a very simple test. If there were multiple tones here, you would see intermodulation everywhere, and that would make things a lot more complicated. So they should warn you about the fact that you overdrive a little bit ahead of time so that they don't wait until the ADC is overloaded. They should warn you once you're above the reference. And again, we can verify this. I can change the attenuation to 10 dB, and you can see that's completely gone. So it's a little minor thing that they can probably change in firmware, but it would avoid confusion for a lot of beginners. Let's take a quick look at the tracking generator performance. In this instrument, you can set the tracking generator power anywhere from minus 20 dBm to 0 dBm, and we saw that it is done during the teardown. Now, you can also use the tracking generator as just a CW tone generator. If you want to use it as a synthesizer, you would set this into 0 span, and then you would get a tone out. Of course, that tone is going to have some harmonic, and that's exactly what we're going to look at. It's unfortunate that you can't set the frequency of the tracking generator independently, because the architecture revealed that you should be able to do this in theory, and perhaps that is something that they can upgrade in firmware. But for now, I'm going to let this sweep in the full span, and I'm going to look how the harmonics move around on a different spectrum analyzer. And here is the tracking generator output sweeping across the screen. I have slowed down the SVA so we can see it move slowly across, and we can analyze the harmonics as they go along. You can see this is the fundamental tone, and it's going to go as high as 3.2 gigahertz, which is the maximum frequency of the SVA. There are some other tones that move backwards. The tones that move backwards are because we're mixing two different synthesizers together, and therefore some of the images will move the other way. That's to be expected. but the biggest distortion tones are from the second and third harmonic. So the total harmonic distortion of this tone is actually not that bad, considering that these are just the second and third harmonic, and all the other spurious tones are quite a bit lower. You're getting about maybe 40 dBc of rejection from the other tones. So it's a fairly good tracking generator, allowing you to use it as a standalone synthesizer in a lot of different applications, which is what you're looking for. Let's go ahead and try measuring the SVA's internal phase noise. In order to do that, I'm going to use the Signal Hound's PNCS1, which is a phase noise reference. I've done a full teardown and review of this. This guy generates a 1 GHz tone at 10 dBm. Except that this is such an exceptionally clean source, there is only one instrument in the entire lab that can measure this thing's phase noise. And therefore, whenever you connect this to a different unit, you're measuring the internal phase noise of the other instrument. That's the purpose of this unit over here. Another really cool feature of the SVA is that it supports full mouse and keyboard support, which is fantastic. I wish more vendors actually brought full mouse and keyboard support to their units, even if it doesn't run Windows. So let's go ahead and set everything up. Since the power coming out of the unit is 10 dBm, we're going to change the amplitude reference over here so that we don't saturate the unit. There it is, it's 10 dBm right over here. And I'm going to change the center frequency. So the center frequency should be 1 GHz, so enter 1 GHz over here. There we go, and we're going to change the span to something very small. Let's say we're going to put a span of 1 MHz so we can really look at the tone. There you go, here's our span. Now the resolution bandwidth is fairly large over here, so let's go ahead and reduce the resolution bandwidth to something quite a bit smaller. This is okay. Now there's a lot of variation here, there's a lot of noise in the spectrum, so it's good to average everything. We can average that fairly easily. We go under trace and I'm going to enable averaging. Now we can wait for a while. I guess 100 averaging is fine. There it is, so it's going to averaging. You can see that it's counting the averaging over here. It's going to become more and more smooth. Now we did a marker to measure the marker noise so we can see how much noise there is in dBm per hertz. We can do that very easily as well. Here's our marker, and I can move the marker anywhere I want, and I can type the value of the marker. So there you go, 1.0001. I wish this wasn't in the middle of the screen. This is not a good place for it. It's better if it was on the left side. I don't know if there's a way to change this, but that's not a good choice here. There you go. There it is. Here's our marker. So our marker is now sitting at a 100 kilohertz offset. Now this is measuring minus 60.9 dBm. That's not what we want, of course. We want a marker function, and we're going to enable noise marker. Now we're getting the amount of power in a 1 Hertz bin at a 100 kilohertz offset, and you can see it's minus 83.1 dBm per hertz. Given that the tone is at 10 dBm, the phase noise at a 100 kilohertz offset therefore is minus 93.2 dBc per hertz. It's very close to the spec. The spec is about to be something like minus 95 or so, so it's a couple of dB short, but it's really close. And the shape of the phase noise can be observed here. The shape can be changed by the PLL coefficients programmed into the Hittite PLL I showed you earlier, and as well as the other ZCOM VCO with the PLL that's tied to that. So this can be modified, of course, and it may change depending on what kind of coefficients and what kind of resolution bandwidth and span that you have chosen. I'm not going to go through all of the different combinations, but this is fairly close to the spec. So here's a setup for our next experiment. I'm interested in measuring, characterizing, and optimizing the performance of this mini circuit amplifier. This is an amplifier that's supposed to work from 10 MHz to 2.7 GHz, right within the range of the frequency response of our network analyzer, spectrum analyzer here. So I'm going to show you a couple of quick things. First of all, I've already calibrated it. I'll just show you how easy that is. And then I want to see what we can do to measure the return loss at the input of this particular amplifier and how we can optimize it with a tuner and how easy it would be on this instrument here. Calibrating the instrument for S parameter measurement is fairly straightforward. Once you have the instrument connected, you can then go into calibration, and there are a few calibration options. You can either use an eCal, which is made by Siglent. Unfortunately, I don't have that. Or you can choose a few of the built-in calibration standards or enter your own. It's really straightforward, so I'm not going to go through the details of that. You also have the option of doing port extensions, which is very useful, and I'm glad that this is included. It's fairly straightforward to do. It's all done in software, of course. We're not going to use that right now, but it is available if you need to do port extensions. So right now we're looking at S11. This S11 is the S11 of the amplifier itself, and you can see it doesn't look very good. And the reason is because the amplifier hasn't been powered yet, and of course some of the matching network includes the active response of the transistors inside the amplifier. So we're going to turn it on. There you go. As soon as we apply power to the amplifier, you can see that the return loss improves significantly. This is a broadband amplifier from 10 MHz to 2.7 GHz, and I have a marker right over here at 2.7 GHz. You can see the return loss is about minus 12 dB. It's not bad, but I want to improve that. You can also, of course, change the way this is displayed. If you go under measurement, you can then change the format. You can make it phase, group delay, or Smith chart, which is of course very useful. We can do a real and imaginary. There it is. You can see it's got a little bit of a funny fractal pattern going on here, that where the impedance continuously spins around. Has to do with the way it is matched. So there you go. But you can see all of it is surrounding the middle of the Smith chart right over here, which would be the perfect match. And that's normal. I don't know what the deal with this line is over here. And this must be some weird drawing artifact that they have here. But having said that, you can see that it is fairly well matched. But the marker is over here, and what we want to do is we want to bring this point all the way in here. There's a couple of ways to do this. We can do different LC matching networks, but I'm going to use a tuner. So let's look up a tuner and see if we can bring this point into the center of the Smith chart. And here is our tuner. So we're going to adjust this tuner until we get a matching we want at 2.7 gigahertz, and then we're going to lock it in place and then use it going forward. Once you have this set up, then you can figure out exactly what kind of tuning and matching network you need from this tuner in order to then fix the amplifier. But for the time being, we're going to use it in circuit. At the output of the amplifier here, I have a 20 dB attenuator, and then that is fed back onto the spectrum analyzer again, so we can measure the S21 as well as S11. Now, one limitation of this unit is that when the tracking generator is being used as port 1 for S parameter measurement, you cannot change the power coming out, which means always is at 0 dBm. So if you need to reduce the input power to, let's say, an active amplifier, you're going to have to put an attenuator here. Now, this amplifier is okay with 0 dBm, so I'm using it as it is, but just keep that in mind. In order to change the power here, then it becomes a little bit difficult, especially when you have a passive resistive coupler like they do. That's why they probably fix it to 0 dBm. But this is a limitation to keep in mind. Okay, I'm trying to tune this. I've already changed the scale from 2.5 gigahertz to 2.9 gigahertz, so the center is at 2.7, and I'm beginning to tune this. Let's scale this up a little bit in frequency, very gently. There we go, and let's go ahead and tune this port. And there you go, it's getting better. There we go, now we're really close to where we want to be. There, look at that. That is, I would say that is pretty good. That's almost an ideal 50 ohm input now. Let's take a closer look. And here it is, and I would say that looks pretty good. You can see that we're around minus 40. Now I can go back to the Smith chart again. Now the Smith chart is going to look only at this confined frequency space. There you go, Smith chart. I'm going to do real and imaginary. There it is. Look at that. There is our 50 ohm line right there. And if you look over here, it tells you what the impedance at that node is. It's 51.1 ohm and minus 82 milliohm, which corresponds to 300. Oh, it jumps around quite a bit. Corresponds to about maybe 100 picofarad or so. So it's fairly well matched now. So we can see how easy it is to use the active S parameter plot as well as the magnitude to be able to bring you to where you want to be. So let's assume now that the input is matched, and I want to look at the S21 of the amplifier over the broad frequency range. And here's the broadband matching again. You can see how well we're matched here. Let's go ahead and add another trace. Under the trace, I'm going to add the number of traces to be 2. So now we have 2 traces, and I can set the second trace to be something else. I can go over here, and I can say which trace we're talking about. Let's talk about trace number 2. And on trace number 2, I'm going to change what we're measuring, and we're going to measure S21 on trace 2. There it is, and there's our S21 measurement. Now this looks really close to 0. The reason is because we have a 20 dB attenuator. But if I go ahead and add a marker to trace 2, and I put the marker at 2.7 gigahertz, you can see it's sitting at 0 dB, which means that we have 20 dB of gain from our amplifier. Now you can mix and match 4 different traces here and look at 4 different parameters. You could look at phase on the Smith chart, on the log magnitude. You can do all kind of different things with these 4 traces at the same time. This is very handy. You can also click on these, I believe. Yep, you can click on them, you can select them. You can of course touch the traces. This is a touchscreen as well. So they've done a fairly good job to make a nice, reasonably configurable S parameter environment for you to make all these measurements at the same time. You can also look at the phase of S21, of course, and take a look and see what kind of phase response we have. We can try that. Let's change the scale. Look at the phase. There it is. That's the phase of our amplifier. This is exactly what you would expect. This is of course wrapping, but you can see we have a reasonably linear phase, reasonably good group delay. You can also look at the group delay of this amplifier right here. You have this is a 1.2 nanosecond here. You can auto scale everything and look at it in detail. I just want to show you an overall capability of the unit. I'm fairly happy with the S parameters. So let's say now we have this amplifier and we want to put some signal through it and see how the amplifier behaves. So the advanced measurement package that you can get with this instrument gives you some of the most important measurements and characterization tools you need for a wide range of applications. So we have channel power, ACPR, occupied bandwidth, TOI, and so on. There's another page with CNR and harmonics. These are measurements that you can essentially do manually, but having them built into the unit reduces the time of making the measurements significantly. So most people basically use these functions. So let's go ahead and try it and see if we can measure the output intercept point of our amplifier after it's been matched. And right now you can see that I'm centered at 2.7 gigahertz once again. I'm going to put a two-tone signal using my Agilent EXG into the amplifier. Here it is. There's our two-tone. You can see it looks very nice. And the two tones have some basic characteristics. Their amplitudes are identical. You can see our intermodulation product amplitudes are also identical. We can see our LO leakage from the EXG, which is excellent. Look at how much rejection of the LO there is, and I haven't even calibrated the EXG. Let's say I want to measure now the TOI. Well, it's just as simple as just click on the TOI, and the instrument will figure out the tones, the spacing. It will report the upper and lower frequencies as well as the TOI for each one. You can see that this amplifier has a YP3 of about 23 dBm, which is not bad. It's okay. And I can go ahead and increase the input signal and see if we can confuse the instrument. There you go, until the higher order harmonics come up. There you go, higher order intermodulation terms have already come up, and you can see the instrument is not getting confused, which is quite good. And we can also see that the TOI has suffered because we're saturating the amplifier so much by putting so much signal in it. Now I've already removed the 20 dB attenuator from the instrument, and that's why the signal power is so much higher. So you can see that making these kind of measurements can be really, really easy. Now let's do something more complicated, like let's say ACPR. So let's do some more characterization here. Right now I have a CW tone at 2.7 gigahertz, and I'm going to replace that with a modulated signal. I'm going to use a 5 megasymbol per second 32 QAM modulation with a root raised cosine coefficient filter of 0.5. So let's go and enable that. There it is. Look at that. It looks very nice. It's a little modulated signal over here. So this is 5 megasymbol per second with 32 QAM. That's about 25 megabit per second. So it's nothing really high frequency or high data rate, but it is very useful for a lot of IoT applications, say. So I want to figure out how much bandwidth am I occupying where 99% of the power of the signal has been captured. Well, I can just select that. There it is. You can see it tells us automatically that with a 99% power, you're occupying, first of all, you're transmitting 1.3, 1.4 dBm of power, and the occupied bandwidth is about 6.3 megahertz. And that makes sense. If you think about that, with a 5 megasymbol per second and a root raised cosine coefficient of 0.5, this sounds about correct. So you can see how easy it is to measure this. Now let's say I want to find out how much of my power is leaking into the adjacent channels. So let's go back and change this to ACPR. Now I'm going to have to set up the ACPR based on the channelization I'm interested in. Let's say my main channel, that we already know how much bandwidth we are occupying, let's say my main channel is 6.5 megahertz. And then my adjacent channels are also, let's say, about 5 megahertz each. At the same time, I want my adjacent channel to be about, let's say, 7 megahertz away from the main channel. There it is. You can see that the amount of power captured here is shown as the left and the right channel, and it also tells you what is the relative power of the adjacent channel to the fundamental. And you can see it's at basically the noise floor right now. But I can change that by increasing how much power comes into the device. Let's go ahead and try it. We're going to increase the power. And eventually, you can see the nonlinear terms begin to leak into the adjacent channel, and we are going to suffer. There it is. You can see our dBc measurement of our ACPR is now minus 33 because the nonlinearity of the amplifier is now leaking into the adjacent channel. ACPR is a critical measurement. If you don't meet the mask for ACPR, you would not even be allowed to put some products that transmit wirelessly onto the market because you would be occupying someone else's channel. So you can see that these measurements can be done fairly easily using this instrument. There's also a spectrum monitor measurement, which continuously monitors the spectrum. You would expect it's a waterfall display. You can change some of the settings of it, but it's basically mostly just going to flow with the measurement that you're doing. So for example, if I turn off the modulation, you can see that we get a very hot spot over here because the signal amplitude is so much larger. And if I go ahead and change the frequency, I can make it jump around. There you go. You can see I can do some basic measurements like this. These are very, very simple. There's nothing unusual here. And these kind of measurements are available with waterfall displays. You don't really have too much control over this. You're basically limited by the refresh rate of this waveform. So it's going to go faster if you change the resolution bandwidth. But you're basically getting a very simple waterfall display. So now that I have the modulation displayed and I know some of the characteristics of the amplifier, let's say I want to do live demodulation. Now this Siglent SVA doesn't give us a real-time spectrum analyzer, but it does have an analysis window where you can do demodulation, which is quite nice. So right now I have a 2.5 megasymbol per second signal coming out. This is a 64 QAM signal, and I want to analyze it. So I can go under mode and I can change the mode to modulation analyzer. There it is. Now in the modulation analyzer you have a wide range of options. You can do AM, FM, ASK and so on. You can even do QAM. And right now I have set it to the maximum available bandwidth. You can see it can analyze up to 7.8 megahertz, and that corresponds to roughly about a 2.5 megasymbol per second it can analyze. And depending on, of course, the filter coefficients, it will occupy less or more of that bandwidth. So it seems that the maximum I can do is 2.5. So if I go over here and try and enter, let's say 5 megasymbol per second, it doesn't let me. It will jump back to 2.5. Now this is a wrong modulation format, of course. This is not, it shouldn't be 16 QAM, it should be 64 QAM. Let's go and select that, and there it is. Look at that, it locks to it instantly. We see a nice I diagram. It must be either I or Q. It doesn't tell me which one. And then you can see the table that tells you how well this modulation is behaving. Now it says the EVM is about 1.3%. That's an SNR of 32 dB, which is quite good. Now one complaint I have here is that it becomes really slow once I try to increase the measurement length, which you have to do if you want to get a good idea of how well the instrument, how well the modulation is actually working. So let's go ahead and change this to 2048. And once I do that, you can see how much slower it will become, unfortunately. There it is. There you go. So now you can see how the mouse jumps around, and if I want to change something, I'm going to have to be very careful. It's hard to hit the buttons now. But that's what happens when you have such a long record length, and this is probably all being done in software. But the measurements didn't change. You can see still about the EVM of 1.3%, and everything looks very nice. Let's go ahead and change this to 256 QAM, and we can see how it does 256 QAM, because that's a pretty difficult thing to analyze here. There you go. I'm going to change the modulation format to 256 QAM. There it is. Of course, it loses it here. I'm going to have to go and select 256 QAM here. There it is, 256 QAM. And it can even do 256 QAM. Every once in a while, you can see it loses lock because it's so hard to do clock ended recovery on this complex modulation. And if you look carefully, every once in a while, you can see that the phase noise of this Siglent SVA is beginning to be a bit of a limitation on this modulation. The phase noise of the Agilent EXG is quite a bit better. But the EVM shouldn't change. It sometimes jumps up and down because it loses lock on the modulation, but it looks good. It's about 33 dB still. So it does a very good job on doing this, and it supports all kind of filters. You can see you can set all your reference filters and measurement filters. So it's very well written in terms of software. It just becomes a little slow when it's boggled down with a long record length and trying to do all this computation. But this can be extremely useful if you need to do demodulation within a 7 megahertz bandwidth, and which is, of course, a lot of IoT devices are going to be using this. So it's good that they've included it. Now, during our measurements, I showed you what happens when you increase the input signal and how the OIP3 of this amplifier suffers. Well, we can see that effect in the modulation too, which is one of the things we can try right now. So let's go ahead and increase the signal amplitude, and then we can see that the power grows continuously. And if you look at the constellation, you can begin to see, oh, now we've just lost it completely. It can't analyze that, but there it is. You can see how the points are being squished out in the corners, and that's the nonlinearity, of course. And the EVM is now all the way up to 6%, and the SNR is now 20 dB. So the nonlinearity that we saw by compressing the amplifier, you can, of course, see that exact same behavior in the modulation, and you can see how the upper and lower part of the eye diagram on the demodulated signal, the eye is no longer open, and that's why the instrument has a hard time locking to it. So this capability is very good, not just for, of course, seeing that the modulation is working, but to also see what happens in the extreme cases of power and phase noise and so on. The distance to fault measurement capability is also fairly useful. Here I have connected a cable to the instrument that has a fault at around 3.8 meters. And you can see that the peak shows up over here, showing that that's where the distance is to where the signal is being reflected back. This is a hard failure, so it's a complete open, so we have a very good reflection coming back, and you can see it estimates that the distance is about 3.8 meters, which is correct. So this can be really useful, especially if you have antenna installations on a tower and you may have even multiple failures, so you know where to go and look for it. And if the cable is buried, then you definitely want to know where to go and dig. You don't want to dig the whole cable out. So this is a pretty handy thing. It basically just uses S parameters at its core, applies the mathematics to it to give you this. But I appreciate that this is built into the instrument now. Well, I hope you enjoyed this extensive review of the Siglent SVA1032X. I think it's a really nice instrument. It'd be hard to find something on the market with the capabilities of this unit at this price. So this thing costs just over $3,000 for the 3.2 gigahertz version, and you can buy up to about $1,800 or so of additional options and software features on it to basically get the instrument that I reviewed here today. So about $5,000. This is US dollars, of course. And I don't think there's anything else on the market for this kind of performance. It performs reasonably well. There are some limitations, and there are some instruments on the market that do better, but of course they're going to be quite a bit more expensive. So for an all-around lab usage, or for some beginners and hobbyists, or for radio operators or people on the field who just want to do some quick measurements, I think it's fantastic. If they can fix a couple of little minor bugs in the GUI, and if they can improve the tracking generator and potentially having it to be independent of the sweep, then you would get a synthesizer, and then you can do offset tracking and do mixer measurements, and makes this quite a bit more valuable from that point of view. So a nice all-around instrument on the bench. I really don't have much complaint about it. Well, if you like this video, please let me know in the comment section. Let me know what you think about this unit. And if you do end up buying something like this, please let the vendors know that you watched my video. I don't really get anything in return for it. This is just so that they would know that you guys are benefiting from these videos, and they influence your decisions for what instrument to purchase. Well, I'll see you in the comment section.